projects. In this video, we are going to explain about the project title Sensing of Particulate Matter PM2.5 and PM10 in the air of Tier 1, Tier 2 and Tier 3 cities in India using EVDHM ARIMA hybrid model. Introduction. Particulate matter PM pollution is a major concern due to its detrimental effects on public health and society. When people inhale PM, especially PM2.5 and PM10, it leads to severe respiratory and cardiovascular disorders. These health issues can significantly impact individuals' well-being and burden healthcare systems, making PM pollution a social hazard as well. Predicting the concentration levels of PM2.5 and PM10 is crucial for primitive actions. By forecasting these concentrations, authorities and communities can take proactive measures to safeguard public health. These measures include issuing health advices, alerting traffic regulations, or recommending behavioral chances to minimize exposure to high PM levels. The current systems used for forecasting PM2.5 concentrations in a particular region have displayed shortcomings in their effectiveness. They lack accuracy, struggle with incorporating all relevant factors affecting PM levels, or face challenges in adapting to the dynamic nature of pollution sources and meteorological conditions. The project proposes a novel approach by combining the hybrid eigenvalue decomposition of the Hankel matrix EVDHM and the autoregressive integrated moving average ARIMA model. The objective is to develop a more effective and efficient predictive model for PM2.5 concentrations. EVDHM and ARIMA, when integrated, leverage mathematical and statistical techniques to better capture and forecast PM levels, potentially overcoming the limitations of existing models. The project centers its investigation on three specific cities in India: Kolkata, Chennai, and Visakhapatnam. These cities are chosen based on their tier-wise classification, referring to their categorization according to economic development and population size. Analyzing cities from different tiers enables a comprehensive understanding of PM pollution across various urban settings, considering factors like infrastructure, industrialization, and population density, which significantly impact pollution levels. This approach aims to provide insights that can be tailored to different city types for effective pollution management strategies. Objective. The primary goal of the project is to create a sophisticated and accurate model for forecasting PM2.5 and PM10 concentrations in different tiers of cities in India. This includes Tier 1, Tier 2, and Tier 3 cities, which vary in terms of population, infrastructure, and economic development. The project aims to assist both the general public and the state administration in these cities. By forecasting PM concentrations accurately, it enables proactive measures to be taken against the health risk associated with high PM levels. This involves issuing health advisories, implementing regulations, or suggesting behavioral changes to minimize exposure. The project adopts a hybrid approach by combining the eigenvalue decomposition of the Hankel matrix EVDHM with the autoregressive integrated moving average ARIMA model. This amalgamation aims to create a more effective and efficient model for forecasting PM concentrations by leveraging mathematical and statistical techniques. To validate the efficiency and robustness of the developed model, it is compared with other well-performing models reported in the literature. This comparison assesses how well the new model performs in practical scenarios and against established methods, providing insights into its superiority or comparative strength. Statistical parameters such as accuracy, precision, recall, and FN score are calculated to assess the performance of the developed model. These metrics help gauge how well the model predicts PM concentrations compared to actual values. Accuracy measures overall correctness, precision assesses the model's exactness, recall evaluates its completeness, and the FN score combines precision and recall to provide a balanced measure of performance. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following steps. The first step is importing the packages. In this step, we import the necessary Python libraries and packages. These include NumPy for numerical operations, Pandas for data manipulation, Matplotlib and Seaborn for data visualization. The imported packages cover a range of functionalities required for data handling, processing, and machine learning. Exploring the dataset. Air quality data. This phase involves loading and exploring the dataset containing air quality data. It includes information about PM2.5 and PM10 concentrations in Tier 1, Tier 2, and Tier 3 cities in India. Exploratory data analysis techniques are used here to understand the structure, contents, and basic statistics of the dataset. Data processing. Pandas data frame. The data is structured into Pandas data frames, which are powerful data structures allowing manipulation and analysis of tabular data. Keras data frame, possibly a reference to data formatting or structure compatible with Keras, a deep learning library in Python. Dropping unwanted column, removing columns or features from the dataset that are not relevant or needed for the modeling process. This streamlines the data and helps in focusing on essential information. Visualization using Seaborn and Matplotlib. Seaborn and Matplotlib are visualization libraries in Python. This step involves creating various plots, charts, or graphs to visually represent the air quality data. Visualization aids in understanding patterns, trends, and distributions within the dataset. Label encoding using label encoder. Label encoding is a technique used to convert categorical data into numerical format, which is necessary for some machine learning or deep learning algorithms. Label encoder is a function often used in Python from the scikit-learn library for this purpose. Feature selection. This step involves identifying and selecting the most relevant features or variables that significantly impact the prediction of PM2.5 and PM10 concentrations. Feature selection aims to improve model performance and efficiency by using only the most influential factors. Splitting the data to train and test for deep learning. The dataset is divided into two parts: a training set used to train the EVDHM ARIMA hybrid model and a testing set used to evaluate its performance. This split is crucial to assess how well the model generalizes to unseen data. Building the model. This phase involves constructing the EVDHM ARIMA hybrid model using deep learning techniques, possibly with Keras, and statistical methodologies. The model is designed to forecast and sense PM2.5 and PM10 concentrations in different tiers of Indian cities based on the processed and prepared data. Training the model. This stage involves feeding the prepared and processed data into the EVDHM ARIMA hybrid model for training. The model learns the patterns and relationship within the data to make accurate predictions of PM2.5 and PM10 concentrations based on historical information. Flask framework with SQLite for sign up and sign in. Flask is a Python web framework used for building web applications. In this case, it's employed for user authentication, sign up, and sign in. SQLite is a lightweight relational database often integrated with Flask for managing user accounts and credentials securely. User gives input, has feature values. Users interact with the web application by providing input values. These input values are the parameters of factors related to environmental conditions, geographical data, or any other relevant information necessary for predicting PM concentrations. The given input is pre-processed for prediction. The input provided by the user goes through pre-processing steps similar to those performed on the training data. This includes formatting, cleaning, and transforming the input data to ensure it's compatible with the model's requirements for prediction. Trained model is used for prediction. The pre-processed user input is then fed into the trained EVDHM ARIMA hybrid model. The model uses the learned patterns and relationships to predict PM2.5 and PM10 concentrations based on the user's provided feature values. Final outcome is displayed through front end. The predicted outcomes PM2.5 and PM10 concentrations based on the user's input are displayed on the application's front end. This could be in the form of graphical representations, numerical values, or any format suitable for users to comprehend and utilize the predicted information. Algorithms used to implement this project, we have utilized the following algorithms. The first one is ARIMA, Autoregressive Integrated Moving Average. ARIMA models capture the linear relationship between an observation and lagged set of observations, autoregression. It uses past values to predict future values based on the assumption that the future is influenced by its recent history. ARIMA models difference the time series to make it stationary, ensuring a stable mean and variance over time. This helps in removing trends or seasonality in the data. ARIMA accounts for the relationship between an observation and a residual error from a moving average model. It models the dependency between an observation and a residual error from a moving average of the lagged observations. ARIMA, known for its effectiveness in time series forecasting, is integrated into the hybrid model to capture the linear relationships, trends, and seasonality present in the PM concentration data. LSTM, long short term memory. LSTM is a type of RNN designed to address the vanishing gradient problem, allowing it to retain long term dependencies in sequential data. LSTMs use a system of gates to regulate the flow of information. They have memory cells that can store and access information for long durations, making them suitable for time series data where long range dependencies are crucial. LSTMs excel in capturing temporal dependencies, retaining information over extended sequences. LSTM, a powerful deep learning model for sequence prediction, is used to complement ARIMA by capturing complex, nonlinear patterns and dependencies in the PM concentration data that ARIMA struggled to capture. As an extension, we applied an ensemble method that combines the predictions of multiple individual models to produce a more robust and accurate final prediction. Also, as an extension, we built front-end using Flask for user testing with authentication. Comparison graphs. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions. True positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm which is best performing in all the performance metric, will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flash framework will host the application locally at the default address. Localhost, which is this, and port, which is this. Now copy this local link provided by the Flash framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So here we need to enter all these parameters to predict the air quality. Before entering the parameters, let us understand the parameters. So the first one is season, refers to the time of the year or meteorological season during which the air quality measurements were taken. PM2.5, particulate matter with a diameter of 2.5 micrometers or less, a pollutant originating from various sources. PM2.5 AQI, air quality index measuring the pollution level based on PM2.5 concentration. NO2, nitrogen dioxide, a gas emitted from combustion processes measured for air quality assessment. NO2 AQI, air quality index reflecting the level of nitrogen dioxide pollution. NH3, ammonia, a gas emitted from agricultural activities, industrial processes, etc. NH3 AQI, air quality index evaluating the pollution level due to ammonia. CO, carbon monoxide, a colorless, odorless gas released from incomplete combustion. COAQI, air quality index indicating the concentration of carbon monoxide in the air. SO2, sulfur dioxide, a gas emitted from burning fossil fuels containing sulfur. SO2 AQI, air quality index measuring the pollution level due to sulfur dioxide. O3, ozone, a secondary pollutant formed by chemical reactions. O3 AQI, air quality index assessing the concentration of ground level ozone. VOC, volatile organic compounds, carbon based chemicals evaporating into the air. VOC AQI, air quality index indicating the concentration of volatile organic compounds. AQI, overall air quality index combining various pollutants indices to evaluate overall air quality. Now we will enter the parameters. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result, air quality is good. Now we will enter another set of parameters and check the air quality. Click on home. So here I'm entering another set of parameters. So here I have entered another set of parameters. Now click on predict button. Here we can see the result, air quality is satisfactory. Now we will enter another set of parameters and check the air quality. Click on home. So I'm entering the parameters now. So here I have entered another set of parameters. Now click on predict button. So here we can see we got the result, air quality is moderate. In this way, by entering the parameters, we can predict the air quality, whether it is moderate, satisfactory or good. Now click on sign out button here. Conclusion of the project. The hybrid model effectively predicted and sensed PM2.5 and PM10 concentrations in Tier 1, Tier 2 and Tier 3 cities in India. It employed a combination of eigenvalue decomposition of the Hankel matrix EVDHM and the autoregressive integrated moving average ARIMA model to achieve this. The model exhibited high efficiency and robustness, proving its reliability for real-world applications. It outperformed other existing models documented in scientific literature, indicating its superiority in accurately forecasting PM concentrations. The project concentrated on 3 specific cities in India: Kolkata, Chennai, and Visakhapatnam. These cities were selected based on their tier-wise classification, considering factors like population, infrastructure, and economic status. This focus enabled a nuanced understanding of PM pollution across different tiers of urban settings. The model's development offers valuable insights for both the public and state administration. By forecasting high PM concentrations, it allows for proactive measures to mitigate health hazards. These insights include issuing health advisories, implementing regulations, or suggesting behavioral changes to minimize exposure to high PM levels.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.